And here we will discuss about further criterion of estimation. So one criterion we had already discussed about, that one was efficiency, and that we use to measure through some kind of loss function or criterion function. So generally loss function is defined with the help of a special kind of norm, and I had already discussed about various norm, that p norm kind of things. And the simplest norm that you are aware of, that norm is simply, you can say that it is a generalized distance, because you are defining distance in higher dimensional. It is not like one dimensional. So in higher dimensional, so you need to know some kind of metric. So that norm is giving one metric, or the simply we can say that generalized distance. And various norm I had already defined, and the simplest norm that you use to be aware of since your high school, that we are calling it L2 norm, or 2 norm, or quadratic norm. There are various names, you can say that. So that norm you use to, or Euclidean norm. So Euclid, actually he is treated as father of geometry. Initially he came up with a concrete idea of geometry, how to stabilize things and how to make things in a very compact way. So he came with that. So that's why Euclidean, just to give respect, also L2 norm, so you can call it Euclidean norm as well. So coming to outline of this lecture, first I will again talk about few more things about efficiency, because this one is one of the major criterion to know about estimator, or estimate what you are going to estimate. So you need to know. So that's where we will talk further. So in last class we had already seen that we talked about efficiency of three estimator, and that time we were very much confused which one is the best one, because so that's why we have to define few more efficiency measure. And we will talk about later sufficiency. So that means whether, if you are having an estimator, then whether that estimator is sufficient to describe the parameter, or we need to go further. So such kind of criteria we will discuss. So sufficiency will come here. That means definitely you will confuse with that. If you suppose someone is saying that we are having a population and we are willing to what calculate, compute mean kind of things, that mean height, mean weight, or mean IQ, or mean some mean population mean, some kind of mean. But we can't do that due to infeasibility to deal with every member of the population. So what we do sampling. So if you do sampling, then definitely several estimator are coming. So among those several estimator, which would be sufficient to describe all those. So from the sufficiency perspective of the estimator also we will discuss a lot. Okay. After that, I will talk about once we are having an estimator, whether that is estimator is consistent in long run. That asymptotic nature we will talk about. That long run in sense that if we will keep on increasing the sample size, where does that estimator will go? Then we will talk about convergence of the estimator, because here sample happens to be what a sample we are taking of various size. And what that if you take sample of various size, that means you are getting various estimator. That means you are getting a sequence of estimator. So if you are getting a sequence of estimator depends upon various size of the sample, then you have to talk about convergence, where that estimator is going to converge. So convergence is just not difficult thing that you know from convergence of sequence, or convergence of series. Those kind of things are coming, that you are aware of from math 1. So that's where math 1 you had already gone through rigorously, that way, so that you can use those a skill what you developed during math 1. So those are knowing convergence of sequence and other things, those are skills. And here problem is coming, that you have to establish that once you are having one estimator, you have to establish that whether that estimator is consistent or not. So those things are your project or your target. With the help of your mathematical skill, you would like to establish that. So that is the job. So that's why you are going through several mathematics classes. Now, coming to efficiency of efficiency. So in last class, I discussed about one example in which we compared three estimator of a distribution. So that distribution was unknown to us. We were not aware of that distribution. That means we want to estimate that that distribution of the data. Data came from the some distribution, but we don't know what is the source of that data. So we want to estimate that source. That we want to estimate that distribution from where that data might come. So we come with several policy of estimating. So one policy through policy we came with the first estimator one, and here you can observe that it looks like we apply the uniform policy, that uniform, it looks like you can say that this estimator is what it is having uniform distribution that you know from probability class. And if you take uh, estimator 2, then this distribution of this estimator, it is having left skewed normal kind of things. It is not normal, ideal normal, so something like that, approximate normal, you can say that. And there is a third estimator, that one is having very near to normal kind of distribution. Okay, so three distribution estimator are having different distribution. Okay, but we want to estimate actual distribution, and we are having idea that actual distribution would have this mean, theta would be the mean of that. So what is happening, that we will try to find it out that which of these estimator are biased or unbiased, first criteria. So criteria of biasness, I had already discussed that. So from the picture itself you can see that if you try to find the mean of the estimator 1, that would matches with theta. Theta is the actual uh, mean of the distribution, but you don't know the distribution, but you know that theta is the mean of that distribution, that you know. So that's why we observe here that expected value of the estimator 1 is directly equal to the value of parameter. So we can say that 1 is unbiased estimator. Now second, also we can say that if you take 2, and here if you try to find expectation of this mean of this estimator, then definitely that one is also equal to theta. So we can say that one estimator 1 and estimator 2 both are unbiased. Why? Because both are satisfying that you can call it this one is 4, you can denote it by capital theta 1 cap, and you found the mean of this one is also equal to theta. This one you denote it capital theta 2 cap. Okay, so both are unbiased estimator. But if you look for estimator 3, then it is not a unbiased estimator. Why? Because if you will find mean will come here, and this mean, that means mean we generally denote it by expectation of this one is the third estimator, so we will write it capital theta 3 hat. So here mean is coming, and this is having a positive biasness. That means it is right away from the actual value of the parameter right away. So that's why estimator 3 is what positively biased. So not good. If biasness is there, so it would be not a good estimator. But if you are having another criteria, that efficiency we measure it through variance. So if you look for variance, what we observe that estimator third is having the smallest variance, smallest mean square error. Also you can say that smallest mean square, it is 3 is having the smallest mean square error. Why? Because you can see that variability is up to here and variability is up to here, a small variance. And bias is also not big bias, it is just near to theta. So that's why in total, so variance and bias in total together, they are forming what mean square error. So you can say that estimator 3 is having the smallest mean square error due to a very small variance. But if you look for variance of 1 and 2, then 2 is having the largest variance. You can observe 1 is having the largest variance, uh, and 2 estimator 2 is having relatively less variance than estimator 1. So among 1 and 2, we can see that 2 is more efficient than 1. But here directly we can't compare 1 to 3 in together, because 3 is, if you want to compare, then 3 is bias, and from the bias that bias perspective 1 and 2 are very good. And if you try to go to measure the mean square error, that means efficiency through mean square error, what is happening that here problem is that 3 is the best one from the that perspective. So definitely you get confused to which one you have to proceed with, which estimator would be better one. So that's why we need to introduce another efficiency measure that we are calling it relative efficiency. How we define it? So what we do, it is difficult when in last case we have already seen that it is difficult to prove that an estimator is the best among all estimators. So we need to define a relative concept. So how we define relative concept? So relative efficiency is defined the ratio of variance of first estimator with respect to second estimator. That means simply if you are having two estimator for a parameter, then find the variance of those two. Definitely you will have variance of those two. So take ratio of that, and that ratio will define relative efficiency. And from there you can, if this value is less than 1, then we will say that theta 2 is very good. If this ratio is greater than 1, then we will say that theta that estimator 1 is very good. So that means this ratio, if it is greater than 1, we will say that theta 1 is good. If it is less than 1, then we will say that theta 2, that estimator theta 2 is good. So that is the scenario is coming in with respect to ratio. So again, this test is having, this efficiency measure is having limitation. It deal with only two kind of things, only at a time, only two what we call it estimator. So one example here I would like to take. So take n observation for a sample of size n, then define sample mean and sample median. So uh, in the graph, a simple question I would like to ask here, uh, just recall, it is a very simple question. So I'm asking, taking if a Gaussian distribution, that means a Gaussian random variable or a standard Gaussian random variable or normal random variable, a standard normal random variable, then tell me what is the relation between mean, median and mode? Anyone would like to comment over it? Anyone would like to comment? What is the relation between mean, median, mode in case of Gaussian random variable? I think in probability class I had discussed for EC student. From EC, anyone would like to comment over this? What is the relation between mean, median, mode in case of Gaussian distribution or Gaussian random variable? Anyone? Are you able to listen me, Mike? Are you able to listen me or not? I'm not getting any response. Just anyone try to answer it. What is the relation between mean, median, mode in case of Gaussian distribution? Okay, it is not, your answer is wrong for Gaussian. I'm asking for a specific answer. It is you are giving a general answer. That one is general one. It is not like that one is not true in case of Gaussian. What is happening that in Gaussian, definitely that would true Gaussian. In Gaussian, if you observe, mean, median, mode all are same, because Gaussian is what? It is unimodal. It is having a single model. So model is talking about mode, single model. And Gaussian, if you try to say that Gaussian is what? Symmetric. So in the graph, easily you can say that Gaussian is symmetric about the mean. So symmetry happens with respect to what? Central point. So that one is talking about median. So median would be also this point, and it is unimodal. So mod would be also this point, and this point we know that it is what? It is mean. By default, it is mean. So mean, median, mode, both all three are same for Gaussian. From the, that's why I had plotted the density function of the Gaussian, and from the plot easily you can say that what is mean, what is median, what is mode. So you know that median is what? It is talking about middle one. Median is just middle one. Which point is middle one? So from the symmetry you can say that this point is the middle one, and mode is talking about that which one happens often, which one, or simply if you talk in a layman way, which one is fashion, that mode, mostly in fashion. So which one? So this one is coming, so this one is having the highest mode, so that's where this point is the mode, highest density, so this point would be the mode. And mean, what is mean? What is the central point? This is the central point, so this is the mean. So in the case of Gaussian, mean, median, mode, all are matches. So if you try to define sample mean and sample median, numerically if you calculate for population, it would be same. But if you go through sample, then there would be issue. Then you have to decide which one is the best estimator. Because for Gaussian, we know that mean, median, mode all are same. But if you define from the sample, then from the sample we can't say that all the mean, median, mode would be same. It is not. Because these are just estimator, it is not giving true value, it is giving estimated value. So we have to talk about relative efficiency. So in order to check relative efficiency, we have variance of a sample mean. We know that from the derivation of sample mean, how we derive sample mean, x bar uh, equal to sum of n observation, x1 plus x2 plus. From this definition of sample mean, easily you can derive variance of the sample mean. And suppose that you know that variance of true distribution is sigma square and mean is mu. This information you are having, okay, this information, but you don't know the distribution. From here you simply can't say that what would be the distribution, okay, if you are having idea of mean and variance. So from there we can't claim that it will be, because every distribution is having both that mean and variance, and that's why we can't say what would be distribution. So this would be, so from here using this formula you can easily calculate variance of sample mean. It would be sigma square by n. And if similarly if you are defining median, then from there you can define what is the variance of sample median. It would be pi sigma square by 2n. And if you try to calculate relative efficiency, it would be pi by 2, that means 1.57. So simply you can claim that sample mean is a better estimator than sample median. From here from the relative efficiency you can claim this concept. So that's why this one is also a very important kind of efficiency, but it is working only for two estimator. So here the sample mean is how many? 1.57 times less efficient than the sample median is 1.57 times less efficient than the sample mean. And hence the sample mean is a better estimator for representing a sample from point of estimation perspective, from point estimation perspective. So even if you talk about types of estimation, actually there are two types of estimation. One is point estimation, that means directly we are getting a single point as a estimate. Another is interval estimation. So those are again part of probability and statistics. So those who have gone through that courses, definitely they may have that idea. Another one is interval estimation. So these are types of estimation. Interval estimation, these are very simple kind of things. Point estimation, simply sample mean is giving your point estimation that corresponding to one observed value you are getting x bar. And interval estimation is giving what x bar, you are saying that it lies between some interval. Either you can take this one interval with respect to this one. If you know true mean, then you can say that true mean, your sample mean, it would you can define vice versa, like just first calculate sample mean, and from there you can define an interval plus minus some marginal error will come here. Margin of error will come. So it is defined with respect to sample size and sample variance. Sample or not sample variance, better take it sample standard deviation. It is defined like this way. So it is talking about interval estimation. So that means in place of singly you're talking about point, here you are talking about interval. So you are saying that your sample thing would be in the true mean would be, or true parameter would be in an interval. And from here you are saying that your true parameter is estimated by this single point. Here single value, and here you are getting interval. So that is the two different type of estimation. Coming to further efficiency criteria. Another one is asymptotic. So here we are talking about in long run. If that means long run, that when sample size is increases, you are trying to approximate the population completely. That means let the sample size go to infinity. So that as in that asymptotic nature, what kind of efficiency you will observe that. So we compare two sample statistics in terms of their variance. So here we had already seen that variance of, if you are taking sample mean. So what was the variance of sample mean? It was sigma square by n. So if you go for long run, that means you are increasing the sample size, and here n is coming in the denominator. So definitely that means if you talking about asymptotic nature, that means n tends to infinity. In that case, what will happens? The variance will tend to 0. So in long run, what is happening, that the sampling distribution of the estimator, it will become a what kind of function, direct delta function, or simply a single, it will give a single value, because variance would be 0. So it will just single out the parameter, so if simply I'm asking one question. I took a number, suppose 2. Tell me what is the variance of this number. Anyone would like to answer? What would be variance of this number, single number 2? It is a very simple question. Anyone? What is the variance of 2? I'm taking a number 2 and I'm asking you a question. What is the variance of 2? Anyone? You can put your question there in comment box as well if you are unable to speak. What is the variance of number 2? No. Variance of variance of number 2 is 0, because you are having a single number. So in single number, what you don't see any variability. If you take 1 and 2, then there is a variability. You will take mean of that 1 and 2. What is the mean of 1 and 2? It would be 1.5, and in the neighborhood of 1.5, you observe, if you go left of 1.5 0.5, then you will get 1, and if you go right of 1.5, then you will get 2. So in case of two number, you observe variability, but if you are having a single number, you don't observe variability. If you are having more than one number, definitely you will observe variability of the number. So that's why in that case you will have variance. But if you are taking a single number, so there is, if that one is fixed, a single number is there, so you don't have any variability. Likewise, if I talk about what is the variance of a mean, so variance of a mean, it would be always 0, because that mean happens to be a representative number. It is a single number, so there is no need of go away, deviate away from the mean in order to get all the members of other members of, because there is a single member, so variability would be 0, and hence variance would be 0 for mean. So if you are taking a single quantity, then always variance happens to be 0. So that's why we are talking about. So that's why when we are taking sample size very large, asymptotic in nature, that means variance would what it will approach to 0, and hence we can say that the sample estimator is just directly converging to whatever parameter we are having, converging to that point. That means it is with variance 0. And distribution, if you talk about distribution, so distribution will take direct delta form. You know that delta form is having very big value at only one point, at rest of point 0, it is 0. So that pattern it is taking. So that concept is coming here. So when we look at asymptotic efficiency, we look at the asymptotic variance of two statistics as sample size n grows. When it go to infinity, go up to infinity, it becomes very big. Simply, you can say that. So note that if we compare two consistent estimators, both variances, that variance of first estimator and variance of second estimator, eventually go to 0. Why? Definitely you see in the definition of variance of any estimator, that sample size would always come in denominator with some power or something like that. It will come in the denominator, and if it is coming in the denominator, and you are going to increase the sample size, definitely that variance term will approach to 0 when n tends to increase. For example, again we consider a random sampling from normal distribution. So we are committing sampling from normal distribution, then what we will observe? So the sample mean will have very uh, sample mean it will have a normal approximately normal distribution, and that sampling distribution always happens to be normal distribution in its approximately normal distribution, you can say that. So with mean mu and what variance would be sigma square by n. So you can ask that why it would be mean, because we know that the way we are defining sample mean, that happens to be a unbiased estimator. So that's way, if you try to find mean of sample expectation of sample mean, that would be equal to true mean. It is due to the definition of sample mean, and because it is unbiased, so that's way mean of the sample mean, it would be mu true mean, and variance, if you try to calculate variance, would be sigma square by n. Okay, so here, and we can observe that when you take your sample size very big, then this quantity would approach to 0, so it becomes a single number mu, and hence we can say that it is converging to mu. This one is converging, and median is what this will asymptotically converges to mu through this variance. Variance would be like this way, but here if you try to focus it out, this convergence is a little bit slower, because it is having pi sigma square and 2n. 2n is going. So this convergence, if you try to look from epsilon n definition, then you will see that here epsilon n definition for the convergence of sequence. From there you will see that that's way mean is asymptotically more efficient than median. So anyhow, mean is sample mean is a very good estimator, always better estimator than median. So in two approaches I have already said established that through relative efficiency, also through asymptotic efficiency, you came to see that sample mean is a better estimator than median. Now I will talk about another, that sufficiency, whether if you are defining one estimator, whether that if estimator is sufficient to describe the corresponding parameter or not, or whether we need to go further what we call it estimator. So how we define? So a statistic is sufficient when no other statistics which can be calculated from the same sample. That means we are having option of only one statistics, whether it will be sample mean or something like that. Okay, from the sample. The sample is because sample, it may we don't have if a sample is coming from any source, then we don't have liberty to leverage the types of sample that we want, this kind of sample or that kind of sample. So sample is already, we are not source, we are getting sample from somewhere else. If you are doing sampling from your side, then that time you are master, you can do sampling based on your choice. But is sample generally it is coming from somewhere else, then you can't do much. Then that time what depends upon that what kind of possible statistics you want to define. So you have to look for sufficiency. Okay, so this sufficiency what is happening, that provide any additional information as to the value of parameter of interest. It's this sufficiency provide. So equivalently we can say that the conditional on the value of sufficient statistics for a parameter, the joint probability distribution of the data doesn't alter that parameter, doesn't depend on the parameter. So if you put conditioning on the statistic or estimator, whatever you are introducing by the parameter, then it is not affecting, independency is coming, independent, it is not going to appear. That is we would like to say that suppose we are having one estimator t of x, or simply you can say that parameter or you can estimator t of x. So if you try to find probability, conditional probability, there you put conditioning over x by this statistics and the parameter, then it is this conditional probability is just independent of theta. you can say that if you observe that this conditional probability is independent of theta, the dependency on theta is not going to affect this conditional probability of x given that corresponding statistics, then simply we can say that tx is sufficient to describe that parameter, sufficient to describe it. There is only one is to describe that, we don't have other option. So this is the best one, only one that so we say that tx is a sufficient statistics, and we don't need further estimator, or we don't need further statistics. So the sufficient statistic contain all the information needed to estimate the parameter. So it is okay to get rid of the original data. So what is happening, that we know that in the data from the sample or the data set, we are having only one statistics. So you can forget about that data, and that just deal with that statistic, and that would contain every information of the data, because the data is having only one estimator. So it is enough to describe about that data by using just estimator. If one estimate data is having more than one estimator, then you will face problem. You have to see comparison which one is the best one, but that data set is having only one, so you can just put the data at place and just proceed with estimator. So while okay, so we need to visualize how to visualize sufficiency. So consider for example Markov chain. Markov chain is a very simple kind of random process. You can observe that it is talking about that chain word is coming with respect to a state. If a state is happens to be a finite state or countable state. So countable or discrete, that I had told that take like finite state, and you are defining over those state you are defining. So finite state you are going 1 to this would be a small. So it is a random process with a finite number of state, and we are having a random process, that stochastic process or random process. We are defining xn, all these are observation. So x1 x2 x3, all these are observation. Okay, so x1 x2 x3, all these are taking value from the state at a party, or simply this n you can say that temporal variable. If you try to model evolutionary process with the help of Markov chain, then you can count n as a temporal variable or time variable or time frame also, you can say that. So here we are willing to estimate theta, the parameter theta, then condition on middle part of the, so this is the middle part. It is one statistics we have defined over this observation, okay, or this sample. Middle part, the front and back. The front, this is the front and this is the back, both are independent to each other. Condition on that, and that one is also property of Markov chain. Markov property, you might be aware of that. So in independency we observe. So given this, if you try to measure dependency of this one with respect to this theta, then you observe independency. So conditional simply you can say the conditional random variable, this given this with respect to this is independent of theta. Due to this, that one is actually Markov property. So that's where nothing special is there. It is just Markov has defined this property. So this one is happening due to Markov property. So it is just Markov property. When you deal with a random process with Markov property and you do estimation by default it would be sufficient. So further, if you talk about, so consider this is the parametric form of density of one random variable x, because we are having sample, we don't know the exact distribution, actual distribution, just we are having few data or sample. So that's why we try to parameterize in order to know want to know what would be the exact distribution. So that means we need to calculate the theta, what would be theta, we need to estimate theta, okay, and qt theta, again we are having statistics, but also we don't know the exact distribution statistic. Why? Because we don't have idea of distribution of x, so simply we can't say what would be distribution of function of x. So that's way. So qt, so we need to parameterize that with theta. So parameterization approach what we are, and from there we try to estimate theta. Okay, so then t of x, this is, it would be an sufficient statistics for theta if for every x in the sample space the ratio, this ratio, it would be independent of theta. Simply you can say that it would be independent. This, if this ratio is independent of theta, then we can claim that the corresponding statistics would be a sufficient statistics. So this you can say that it is what one computational approach to validate whether one given estimator is a sufficient estimator or remember that many times I am saying that estimator, many times I am saying that statistics. So all estimator happens to be statistics, and I told that statistics is what? It is a function of random variable. Function random variable happens to be here observations, and from why do we do observation? We order to take a sample of size n, and our ultimate objective is to estimate parameters. So that's why we do sampling, and we are defining statistics, and name of that statistic is estimator. So sometimes I may call it estimator, sometimes I may call it statistics. So there is no issue. Statistic is very general and estimator is very specific. So here, in order to validate whether one estimator is sufficient or not, so took the ratio and try to find it out whether it is independent of theta. If it is independent of theta, then simply we can say that the corresponding estimator would be a sufficient estimator for the parameter theta. So in again I will take example from normal distribution. So normal sufficient statistics, we will try to see that here in the case of normal distribution, if you take sample from normal distribution and if you try to define some kind of estimator, definitely that would be a sufficient. So I told that that's where mean, median, mode all are same in case of median, in case of Gaussian distribution. So you don't need to define various kind of estimator, just take one estimator, that one is sufficient to describe the normal distribution. Okay, so that's we take one parameter of normal distribution, that mean or variance, whatever you want to proceed with. Okay, so consider a n number of observation from the normal distribution having mean, mu and sigma square. Okay, in IID fashion, that means independent. IID full form is independent and identically distributed. That means independent, that x1 and x2 both are independent to each other, x2 and x3 are independent to each other. Likewise pairwise independency you are having, and apart from that what you observe that distributed, identically distributed, that means all are copies of the same distribution. That means all are having the same distribution. Why? Because we are doing sampling. We have taken sample from some unknown source, and we assume that all the data are coming from the same distribution. It is not like that it is mixture of distribution. Okay, so that this IID condition is very special condition where the variance is known. So we know what is the variance. We have to estimate. We don't know mu. We have to estimate mu. Okay, so for this perspective, the sample mean what we are defining, it would be a sufficient statistics for mu. So that means here mu is unknown, sigma square we know, and in order to estimate mu, what we don't need to define sample median or sample mode. Just you define sample mean, that would be sufficient to describe about mu. Sufficient. So that's why sample mean is a sufficient in case of this kind of data, if it is coming from normal distribution. And why it is sufficient, that source, you know that mean, median, mode all are same for normal distribution. Okay, now further visualization I will talk about. Let us start with joint distribution function. So that means joint distribution function we will define. That means we are having n number of distribution, n number of observation, sorry, that means a sample size of n, and one value we are observing, a small value, or it would be what? That means it is talking about first observation is coming from x1 is coming from x1, x2 is coming from capital X2. Likewise first and xn is coming from nth observation. So So this is the situation. So we try to find, so we are having n number of observations, so we will talk about joint distribution of these n. So that means we are having n number of random variables, so we are talking about joint distribution of that given mu. Okay, given mu, so we try to find it out. So that means we assume that all are from the same copy, all will have the same mean, so that's why given mean, but mean is unknown to us, we don't know that. Okay, so here this is the way to define joint distribution through IID condition. I had told that x1 is independent of x2, x2 is independent of x3. Likewise, IID condition and identically distributed, that this means every xi is having same mean and variance, same mean. So that's way. So due to that independent nature, from the multiplication rule easily you can multiply all these and to get joint distribution, and if you further simplify it will take this form. Here it is product, pi is talking about product from k equal to 1 to n, and after that simplifying, because it is exponential, so interchangeability between pi, that product, and summation sign is possible, and you can finally put it in this summation form, and what is happening, it is always easy to proceed with summation approach. So that's where this interchangeability is possible, and you just simplified this one like this way, and after that what you do, add and subtract sample mean to see the sufficiency. So here after adding and subtracting, so same, just rephrasing this statement like this way by introducing sample mean. So we have introduced minus x bar plus x bar, so I mean there is no any effect, so just we are rephrasing this density, joint density with respect to sample mean. We try to introduce sample mean. Okay, and why we have to see that this joint distribution, it would be independent of joint distribution with respect to sample mean. Distribution of sample mean, it would be if you condition joint distribution of x with respect to corresponding estimator, and then and also with respect to mean as well, then it would be independent of mu. So that independent nature we want to see. So we need to recall also distribution of sample mean as well, because we have to take ratio of this one. How to compute sufficiency, take ratio of this with ratio of the distribution of sample mean or estimator, corresponding estimator. So this is the distribution of estimator, and we will find the ratio. So like this way, the ratio, if you try to find it out ratio and just do simplification of all these, and simply after simplifying you will come to see that here you don't observe mean. Here in the simplified form you don't observe mu, so simply you can say that this is what, this is the distribution of sample mean. So we can simply say that this ratio is independent of parameter theta or mu. Actually in last case I had taken mu, so you don't observe mu. This theta is mu. Actually we are talking with respect to mean perspective. So this ratio is independent of mu, so we can simply say that sample mean is what, sufficient estimator for estimating mean of the normal distribution, mean of the normal distribution. So that means you are taking data from normal distribution, but you don't know what is the mean. From this sample you can't get exact value of mean, you need to estimate. So that's why you can estimate by defining sample mean, and that sample mean would be a sufficient estimator. So that is the story.